Hi everyone, this is Josh. Today I'm going to be covering UVM-based verification of AHB-MUX, where we just verify arbiter and cache behavior in a multi-master AHB system. So I'll get on with it. The first question might be, what is UVM? Well, UVM or Universal Verification Methodology is a powerful framework used to test hardware designs efficiently and automatically. It is built on System Verilog and helps engineer build modular, reusable, and scalable test benches. As you can see, UVM test bench consists of several key components: the test that sets up the goal, the environment, which includes agents, scoreboards, and coverage collectors. Agents include a driver, which sends data to the DUT, a sequencer, which generates test pattern, and a monitor, which watches the output. The scoreboard compares what the DUT did with what it's supposed to do. UVM makes it easy to generate randomized inputs and run thousands of test scenarios automatically. It also measures coverage, showing how much of your design has actually been tested. In short, UVM is like a test automation framework, but for hardware. It saves time, increases confidence in the design, and is in the industry standard for verifying digital systems. Further, about the AHB-MUX, well, as you can see the diagram, this is an RTL diagram of the AHB-MUX. I'll be discussing this in a bit. So how do you understand what the AHB-MUX is? So the AHB-MUX is a hardware module used in systems with multiple AHB masters like CPUs and DMA controllers that all want to communicate with the shared slaves like memory. Only one master can use the bus at a time. That's where the arbiter comes in. It decides who gets access. If two masters want the bus, the arbiter checks who has the higher priority and whether anyone is using a lock transfer. It then selects masters and outputs a signal like master select. Sometimes the bus isn't ready to accept a request. For example, if H ready is low, in that case, the cache stores the master's code temporarily. Once the bus becomes ready, the cache request is released. So overall, the HBMUX acts like a traffic controller for data, making sure only one master drives the bus and the timing and control signals are perfectly aligned across the pipeline. Now, let's go to the important part, which is the verification plan overview, right? Now that we know what the UVM is and how the AHB-MUX works, let's dive into the core of the presentation. First of all, as you can see, the reset behavior. The first group of tests ensure that everything in the system resets properly when command H reset is deasserted. ARB select, previous, master select, and master select are clear to the default states. This might sound basic, but think of it like imagine starting your car and the dashboard lights are already blinking. Not good, right? So we ensure everything starts clean. Then we go to the arbiter logic. This is the brain of the MUX. The arbiter decides who gets to use the bus. So what do we check for? Master selection. We test that only a master whose H trans is not idle can be selected. Idle means not requesting the bus. Further, multiple masters requesting. If two or more masters require access at the same time, the arbiter should pick the highest numbered master, kind of like a priority. Locked master control. If a master selects H mask lock, it means it's doing a lock transfer. It is a very critical time transfer, and like the arbiter must not preempt this master until it completes the process. Previous master maintained. If nobody is requesting the bus, then the arbiter should not change the selected master. It should stick with the previous one. This avoids unnecessary switching. H ready transition. Even if a new master requests the bus, the arbiter should not switch until the current master is done, indicated by H ready going high. This maintains the pipeline consistency. Previous signals, this is very simple. Once H ready goes high, the previous signals should update to reflect the behavior of the master. Busy master retains control. If the current master is still in a valid transfer, that is, if H trans is busy or sequential, it should remain selected. No bus request. If every master is idle, then the arbiter just waits. This avoids noise or undefined control lines. And lastly, the correctness. We check that the ARB select always reflects the correct value in the master. This ensures that the MUX selects the right line to input forward. Cache behavior. Similarly, we just check if the cache is working on reset, if it's capturing the valid signals, if it's hold during busy, and when we grant the master and the bus is ready, the cache should clear itself. Think of cache as like a bus stop. It's waiting for the bus to come and take it away. H-ready out logic, similarly, we have to check that if it stalls on valid cache, then if it mirrors the H-ready in, if it H-ready when it goes high, when no wait needed, and if there is no cache data and no previous master, we're free to move. H-ready out should go high. Even further, we can also check cache pass through behavior, where we check if cache bypasses when invalid. If the cache is not valid, meaning there is nothing stored, then the address phase signals and downstream out should come directly from the current master's input. Cache retains data between request, cache, and H-ready in. Further, full reset, which is that every signal from arbiter control lines to cache status resets correctly. Further, even with the further thing, address phase master switching, master master cache, address phase master transition, data right with previous master. Further, the slave responses and read data, we check the value of the slave responses and if the data is returning correctly. And last but not the least, is the integration and multi-master sync, which just the final selection ensures that the entire system works when multiple masters are active by checking the multi-master arbitration, arbiter cache sync, and cache isolation. So by walking through these 30 plus checks, we verify that the AHB-MUX handles every expected and corner case. Each of this behavior is modeled in a UVM test driven with random scenarios and checked with scope words and assertions to ensure that duty behaves exactly as it sounds. This is what makes UVM such a powerful methodology. That's all for today. Thank you. If there is any question, you can find me at this email ID.